Hey guys, thanks for coming to the meeting. So I've been going over the books and the hydrofoil sales are on the decline, man. Look at this graph over here. Sales have been going down and I need them to go up, not down. So I need you guys to prepare a report and a new product that our company can use to make our sales go up. Got it?
Understood. We'll get our co-op to do that.
Alright, whatever works. Hey guys, what's up?
Oh hey, it's our new intern, Bob. Finally showed up.
Yeah, how's the meeting, guys? How was the CEO talking to you guys about?
Well, the big guy, he was just talking about how well our hydrofoil sales were.
Wait, what? Hydrofoils?
Well, you don't know?
No.
How do you even get hired in the first place?
Honestly, why are you here? Like, there's their door.
Anyways, let me give you a quick introduction. Hydrofoil, think of it this way. Works similar to that of an airfoil wing. Instead of lifting an aircraft in the air, lifts a watercraft, it's in the water, out of the water.
No, okay.
Same principles.
Yeah, so how come Well, what are the advantages of such a thing?
Well, as your water vessel moves faster in the water, the hydrofoil generates more lift.
Yeah.
And when that happens, the hull of the vessel, the water vessel, is pushed out of the water. And because there's less surface area counteracting, or less surface area on the boat that's touching the water, since the hull is lifted, you have reduced drag and therefore greater efficiency.
Oh, okay. So if it's good for all that, then how come I've never seen a actual hydrofoil boat?
I don't know, beats me.
I don't know.
Well, that's gonna require a quick history lesson. Enrico Forlanini was the inventor of the hydrofoil, which he first started modeling in 1898. Alexander Graham Bell, the inventor of the telephone, also worked with hydrofoils, and in 1919, his vessel, the HD-4, set a marine speed record of 114 kilometers per hour by using hydrofoils to lift the hull out of the water to reduce drag. Hydrofoil use peaked in the 1960s. However, their disadvantages made them less popular. Hydrofoils require complex machinery, are costly, and are hard to maintain. Despite this, hydrofoils are popular amongst hobbyists. The E-foil, for example, is an electric-powered hydrofoil surfboard. Here's a short clip of it.
What we're gonna do right here is go back.
So before we apply numerical methods to solve for an ideal hydrofoil design, we have to make certain assumptions in order to simplify the process. Firstly, we hold a hydrofoil speed at a constant 20 miles per hour, regardless of its depth and location. Also, water and wind conditions are assumed to be constant, with water currents not affecting the foil. Water pressure is also held at a constant 1 atmosphere, as our foil is meant to operate at sea level. The hydrofoil material is assumed to be non-deformable for simplicity. Finally, as the solution is meant to be rideable, the total mass of the hydrofoil and rider can be set to a constant 250 pounds. The shape of a foil dictates the lift and drag that it will produce. These profiles can also be used to determine their stability. The NACA 0012 airfoil was chosen to maximize stability to provide maximum support to the rider. However, to gain stability, lift force and low levels of drag are sacrificed. The 0012 is horizontally symmetric, meaning that the net lift force generated when the foil is moving through the fluid is zero. So an upwards lift force is only generated when an angle of attack is present. The NACA 0012 model is also very convenient as it maintains a consistent curve of its lift coefficient with respect to its angle of attack. This makes it very stable under pressure. To emphasize this, we compared the 0012 to a NACA 0024 airfoil. The difference between the two are their heights, with the 0024 being twice as tall. Notice that the blue curve for the 0024 which represents the effect at lower speeds, is extremely inconsistent with those at the higher speeds. This means that the airfoil becomes unreliable.
So before we get to anything else, we want to first test our simulation software, which will be ANSYS. To ensure that it is an acceptable tool to use, we will design a standard hydrofoil, simulate it, and compare it to external confirmed data. We use the NACA 0012 airfoil, which has an extensive amount of detail on many characteristics, such as the lift-drag coefficients and how they react to varying angles of attack, and their dimension characteristics as well as plots outlining all these properties. We will be validating ANSYS by testing the lift coefficients extracted from the simulation by using the formula shown, and comparing it to the confirmed data. Comparing the lift coefficient is a good method to test ANSYS because it is not dependent on the medium of the fluid, which means that it would give the same results whether it was tested in water, air, or even honey. It should ideally be the same. Also, the lift coefficient relates to our main objective of determining the lift at our criteria of about 1.2 kilonewtons. Now, as you can see on the plot, our simulated lift coefficient results are almost on par with the true data. There exists approximately a 10% error when evaluating the data on the positive angle of attack region, which is good enough to show that ANSYS is an appropriate tool to use.
So we chose method of bisections to solve for our hydrofoil model, since it is robust and likely to converge. Our boundary parameters are the angle of attack, the length, and the width. The range of the angle of attack is between 5 and 15 degrees to maximize lift potential. Most production-ready hydrofoils sold to the consumer market have widths falling between 300 mm to 750 mm, so we set the width range between 250 mm to 1 meter. Finally, the minimum and maximum boundary conditions for the length were set to be 100 mm and 300 mm respectively.
So by varying the hydrofoil parameters individually, we were able to come up with the following results. Between the two tables, it's clear that at a greater angle of attack, there is more lift produced from the same size hydrofoil. To minimize the volume of the foils, let's focus on the second table. Now within our given bounds for width and length, there are many solutions. Although there is around a 2% error relative to the target lift, we will consider it negligible since it can easily be compensated by increasing speed. In fact, if we model the lift as a function of length and width by fitting the given data points using the MATLAB curve fitting tool, we see that there are an infinite number of height and width pairs that give the targeted lift. These can be obtained by the curve of intersection between the shown function and a horizontal plane with the lift fixed at the targeted lift. So to obtain the best solution, we must look at the volume of the hydrofoils, which is seen in Table 3. A general trend seems to appear. As the length of the foil decreases, so does the volume. Therefore, we'll select the foil with the least length, which is still within our bounds.
Looking at the results, you may be asking yourselves why we don't continue to go even lower and evaluate the results at 50 mm rather than remaining at 100 mm. Well, remember that we first assumed the hydrofoil structure to be a non-deformable solid, just for simplification. If we continue to decrease our length in order to reduce the volume, then the foil will become thinner and will be subject to test its own elastic restoring forces. Let us calculate the bending forces on the foil for the two lengths. We are able to extract the moment due to the 1.2 kilonewton force using the shear force and moment diagrams, and by applying the bending stress equation shown, we get 19.5 megapascals of bending stress applied onto the 100 mm foil, compared to a whopping 15.6 gigapascals of stress onto the 50 mm foil. Considering that the yield stress of steel is just under 250 megapascals, it seems like we hit our limit at a boundary of 100 millimeters for our length. Now, the main reason the bending stress rises so dramatically is that the moment of inertia decreases by a large margin since it is a function of the height cubed, and that affects the stress a lot since it's inversely proportional to it.
Now here's a simulation for velocity of water over the final design. As can be seen, the top of the wing has higher speeds of water flowing over it, and the bottom of the wing has lower speeds. This therefore creates the lower pressure on the top of the hydrofoil and the higher pressure on the bottom of the hydrofoil, causing it to rise.
The implications of this project are widespread. We learned that laterally symmetric designs are unideal for maximizing efficiency as the net lift force is zero when no angle of attack is present. This is why the airfoils that are found on aircrafts are never horizontally symmetric. Also, motorized surfboards are becoming increasingly popular. The design of such folds are quite varied, although the results of this project is a design that prioritizes stability. The emphasis on low volume also means that the overall cost of this project would be low. As for future recommendations, we hope to use scripting to automate the iteration process. This would save time and allow for more iterations.
I've been reviewing our books here, and it seems like hydrofoil sales are declining now. Just look at this chart. The sales have been down for months. I need you guys to come up with a report to summarize why this is happening, and I want that.
Oh, I was going so well.
Looking at you, son.
I was looking at the line. And from the corner of my eye, I saw this guy
Coming to the meeting. So I've been going over our company's books, and I've noticed that our hydrofoil sales are on the decline. Just look at this graph over here. Sales are on the decline. Yo, man, that was too much of a struggle for the thing.
Yeah. Hydrofoil works into that airplane wing. Instead of lifting an aircraft above the water, it lifts a watercraft above the water.
Sorry, we're doing a video. We're recording something right now.
This room is out of service and like
Or no, the janitor and the floor on the fourth floor told us we could use it. Well, that's gonna require a quick history lesson.